Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Good evening, everyone. Today, we are privileged to have Dr. Habib as our speaker about fundamentals of biostatistics. Before that, it's this. I just want to highlight that this lecture comes as one of SODAQ commitment, the Sudanese Doctor Association in Qatar, commitment as a diamond sponsor to Siraj Al Sudan competition, which was arranged by the Research and Publication Office at the University of Kariri, and also as part of our commitments with the Khartoum Medical Student Association towards a research mentorship program. So without further delay, I'll just introduce Dr. Habib in a few words. So Dr. Habib, he's a faculty at the Qatar University College of Medicine, and he's a visiting fellow at the Institute of Health and Society at Newcastle University in the UK. He also serves as an adjunct additional professor of health economics at the Public Health Foundation of India. Early in his career, he worked as a research fellow and a postdoctoral fellow at the London School of Hygiene and Tropical Health and surveillance medical officer at the WHO. He obtained his medical degree from the Institute of Medical Sciences, Banaras Hindu University, and non-degree postgraduate from Sydney University. He also served fellowships for research and training from Australia or OSAID, Wellcome Trust, and Columbia University. He supervised more than 30 master's level students and published more than 40 peer-reviewed articles and book chapters, and served as a reviewer and an editor on top international journals. He served as a member of the technical expert on several national and international advisory committees, including the IBRAC WHO headquarters in the UK, and other associations in the States and WHO as well. His research and teaching interests include evidence-based medicine, intersection of infectious disease epidemiology and economics, and health economic with focus on pharmaceutical economics and HTA. One of his core areas of research interest is vaccine in preventable childhood diseases. It's really a privilege to have you, Dr. Habib, with us today with such a rich CV. We're really privileged and honored to have you with us. So without further delay, Dr. Habib, the floor is yours.
Thank you very much, Dr. Khalid. Assalamu alaikum, everyone. So it's a great privilege and honor to be here speaking about the basics of the biostatistics. So in this 1 hour session, it could extend to 1.5 also. We don't know for now. We'll try to cover the basic concepts. We'll primarily focus on the key areas such as types of variables, measures of central tendency and dispersion, normal and the not normal distributions, and sampling variability. For some of you, it might be very basic lecture, and for some of you, it might be a little advanced. But feel free to stop me whenever you think I'm going too fast. So let's start with the basic question: what is data? So if you look deeply, the data is generally a piece of information or pieces of information about observations. You can call those observations as individuals, organized into variables. So by an observation, what we mean is an individual. We mean a particular person or an object, which could be an animal, cell, or a specimen. And by a variable, we mean a particular characteristic of that observation. So for example, it could be age, gender, and height. So let's look at a simple Excel table. As you can see, we have rows in which we have the patient 1, 2, 3. These are individuals or observations. And on the columns, you can see there are variables. And the variables of interest could be different for different research purposes. In this particular example, we are looking at variables such as gender, male or female, age, weight, height, smoking status, and race. And there could be several examples of biomedical data. It could be related to patient information, such as its date of birth, which helps us understanding their age, their sex, entry in the study and exit from the study. It could be routine medical data that we usually collect when the patient first walks in the clinic, such as their weight, height, blood pressure, and biochemical tests such as cholesterol levels, sugar, and others, and also medication use. You could also, for specific purposes of a specific kind of research, could actually collect a specific laboratory data such as genomics, imaging, and others. So, in summary, and this is a snapshot from very important, a very powerful magazine called Economist, which has highlighted that the data is most valuable resource, and especially in the current times of sophisticated machine learning and AI-based algorithms, and all our data that is online, data has become a valuable resource for all the agencies, not only health data, but also other data regarding behavioral interests of individuals. So let's start with what is biostatistics. So biostatistics is basically statistics which focuses on health sciences or biological sciences. But then the question is, what is statistics? So statistics is a branch of mathematics which deals with collection, analysis, interpretation, and presentation of data. So what we try to do in statistics or biostatistics is we collect this data and we convert the data into information. So for example, if you are planning to do a research, for example, that research could be about, say, prevalence of asthma in Doha. You first ask a relevant research question, then you plan your study, then you go on to collect the data, you organize the data, you analyze the data, and then you present the data in a specific format, which could be tables, which could be graphicals, and then you interpret the results. So, in summary, what we should understand is that by converting good data, by using good data, we get useful information, but bad data sometimes gives not only just incorrect or useless information, but it could be harmful information. So, in general, when we talk about biostatistics, we talk about two specific branches of biostatistics. So you can think of it as descriptive statistics and inferential statistics. And as the name suggests, descriptive statistics try to describe the data. So you summarize and display data in a specific format for your audience. Whereas in inferential statistics, you draw conclusion about the population from a sample. So briefly, in today's lecture, we'll talk more about descriptive statistics, summarizing the data, displaying the data, and we'll briefly touch upon the distributions. We will not touch deeply on the inferential part of the statistics, which is the topic of another lecture. So first, let's talk about planning, collection, and organizing data. So for example, you want to know the prevalence of children with asthma in the Doha, but you cannot go and collect data on all the children's in the Doha for this specific question. What you need is a representative sample. You could be that could be a representative sample of all school-age children in the Doha. So the first question is, why can't you do it on the entire population? Why do you need a sample? Well, the simple answer is that you don't have time and resources to collect information on the whole population. It is practically impossible. So what you do is you use a representative sample. But how do you generate a representative sample? So sampling is the framework which helps us create a sample from the total population. So when we have an unbiased sampling, think you can see in the left-hand side, you have, say, imagine that population of 20 children, 16 children are without asthma and 4 children are with asthma. So the distribution of asthma and non-asthma children is 20 is to 80. So if you draw an unbiased sample, what you get is 5 children, one with asthma and 4 children without asthma. That's your unbiased sample, and that helps you generate appropriate statistical inference. But with a biased sampling, you would not get the accurate distribution of asthmatic and non-asthmatic children from the population. So what you do to generate a reasonable and unbiased sample? One of the method is called a simple random sample. There are other methods also, which we will talk about in some other session. But for now, think of the simple random sample as a mechanism which provides each child in the population the same probability of being selected into the sample. So the selection of the child does not influence the likelihood of selecting another child. It is called as sampling independence. So any violation of these two principles, the principle of same probability of being selected into the sample and the sampling independence, could result into a bias sample. Some of the classic examples of biasing is, especially when we do surveys in a population, we see that there are people who are more interested in participating in survey. So that creates a kind of bias. Again, there are people who are not interested in participating in the survey. That creates another kind of bias, which is non-response bias. Sometimes we don't have appropriate sampling frame and children from one of the subgroups or one of the neighborhoods are underrepresented. That again creates a bias sample. So what we need is a simple random sample which is unbiased, which provides equal probability of each child to be in the sample. So once you have the sample, the number of individuals in that sample would be your sample size. And then based on your research question or research interest, you would collect different informations. For this particular example, you are more interested in knowing the age of the child, their gender, their say school, and their exposure to different agents that could cause asthma like symptoms. You would want to collect information on their family history and so on. So again, as we see this table before, you then create that, you fill that information, think of it as Excel sheet, in an Excel sheet where you have information on all the children's and the characteristics that you were interested for. So once you have this information, now you can think of all this information as variables. For example, these variables could be continuous, which can be, you can think of them as numerical or quantitative variables. And these variables could be categorical. You can call them non-numerical. So what is the difference between a categorical variable and a numerical variable? So categorical variables, as the name suggests, are generally categories. So for example, they could be nominal, which represents, say, a name. For example, there could be two categories, say male and female. There could be several categories for ethnicity, Asian, African, Arab, and so on. And among these categories, you can think of situations where there is some kind of order. For example, think of pain. The pain could be an ordered variable where you can check with the individuals how much pain do they feel. Mild pain, no pain, mild pain, moderate pain, and so on. So this is an ordered category. You can think of social class. Social class could be poor people, middle class people, rich people, and so on. But you can see that there is an inherent order in these categories. Whereas the numerical or the quantitative variables can be thought of in two perspectives. One is a continuous variable, think of weight, which can be from 0 kilogram to anything. And you can have fine discrimination between the measurement. You could measure individuals in terms of round numbers as 1 kg, 2 kg, 3 kg. There could be 1200 grams, there could be 1256 grams, and so on. So that have a continuous scale, and it also has an absolute zero. Another numerical variable could be a discrete number. You can think of as number of children. So a mother having 4 children, 5 children, 3 children, you don't have 3.5 children. So that is again a numerical data, but discrete data. Why do you want to understand these variables in these broad categories? Because that helps us use specific measures to present this data. Let's talk about categorical variables. So as we said, there are non-numerical variables. Another example could be blood groups. Individuals have blood group A, B, AB, or O, and they are usually measured on the nominal or the name scale. We talked about another kind of categorical variable, which could have two possible values, such as gender, male or female. It could be disease status. A person could have diabetes or non-diabetic. It could be dead or alive. And we discussed about ordinal variable or the categorical variable, which has some kind of natural ordering. And these are analyzed using frequencies. It could be counts, it could be percentages, it could be proportions, and we present them in table. We'll see some examples as we go forward. Now, as we talked, another variable we talked about was the numerical or the quantitative variables. And again, we said they reflect exact amount and position of observation on a meaningful numerical scale. We talked about continuous variables, which can take any value on a continuous scale, such as age, weight, blood pressure. we talked about discrete variables, which can take limited number of values, generally whole numbers. So you can think of number of diarrhea episodes, number of pneumonia episodes, and so on. And they are generally analyzed using measures of central tendency, such as mean, median, or mode, and spread or dispersion, such as standard deviation and range. Then you can think of other kind of variables such as derived variables. Now these derived variables can be categorical or numerical. Let's take example of body mass index. The body mass index is a derived variable. The reason is that the body mass index is calculated as weight in kgs over height in meters square. So you get a value. So now you are using two continuous variables, the weight and the height, to derive a new numerical variable. And that's why we call it as derived variable. The other way could be you can reorder or create categories of the variables. For example, we know that age is a continuous variable, but you can create age groups for, you can call them children's, you can call them adolescents, you can call them adults, you can call them elderly, and these groupings are now called as derived variables. So derived variables are generally based on specific thresholds. So let's look at this specific example. Now you can see this is state output, and you can see on the rows you have the IDs, and in the columns you have age, gender, smoking, systolic blood pressure, categories of systolic blood pressure, height, weight, BMI, cholesterol, and so on. So you can clearly see that age is measured both as a continuous variable, and age is also explained in categories as a derived variable, now in particular categorical variable. Gender we know is a categorical variable. Smoking status we know is a categorical variable. Again, you can see height. Height is a continuous variable. You can see body mass index, and we just discussed that body mass index is a derived variable. And you can see number of sons each particular ID had. So you can see the values as 1, 2, 3, 4. Now this is a discrete quantitative variable. So once we understand the distinction between these variables, that helps us use summary statistics to present them in appropriate format. Another commonly used terms are called as exposures and outcomes. So if you want to investigate an association between an exposure variable and an outcome variable, your question defines what is an exposure and what is an outcome. For example, generally the outcomes are also called as dependent variables or response variables. And this is a particular variable which we seek to understand. An exposure is also called as independent variable or an explanatory variable. And these are the variables that determine our outcome. Let's take a few examples. So for example, if you are interested in knowing whether mother smoking during the pregnancy leads to low birth weight, so your exposure variable is smoking status, yes or no, and your outcome variable is the birth weight. You could call you could use specific continuous variable, specific continuous scale for the birth weight, or you can categorize as low birth weight, yes or no, depending upon a specific threshold, say less than 2500 grams. If you're interested in knowing whether access to clean water can reduce number of episodes of diarrhea, now your exposure variable is clean water or access to clean water. So for example, do they have clean water? Yes or no? And then your outcome now is number of diarrhea episodes. And this number of diarrhea episodes, as we discussed, is a discrete variable. You cannot have 1.5 diarrhea episodes. You have 1 episode, 2 episode, 3 episode, and so on. Another example could be, does living in a proximity of a nuclear power station, which is measured in miles or kilometers, causes childhood leukemia? So your exposure variable is your living status near the nuclear power station, and your outcome is leukemia, childhood leukemia. So that's how you can use the same classification of variables, and you can classify them as exposure and outcomes. So once you have defined your research question, you have collected the data, you have understood your observations and your variables in detail, you can now analyze this data. So some of the mechanisms or some of the ways how you analyze the data again depends upon how the variable is classified. For example, if we want to create a numerical summary of a variable which is categorical and nominal, that is, say, example, gender. So you want to know what proportion of your sample is male and what proportion is female. You report percentages in each categories. And in terms of graph, you can demonstrate that in a pie chart or a bar chart. Again, if your interest is reporting a categorical variable, which is on an ordinal scale, again, so you want to show the distribution of rich, poor, and middle class population in your sample, you can again report them as proportions in categories in the order. And if you are interested in reporting variables such as height or weight, and you want to report what is the mean weight of your sample or mean height of your sample, you can report them by reporting means and medians, or then dispersion around the mean and the median value by measuring standard deviation and the range. And graphically, you can report them in as histograms or the box plots. Let's look into each of them. So when you want to summarize a categorical data in the tables, you count the number of observations in each category. For example, let's start with a very simple example of number of males and females. You count those observations in each category, male and female, that is called as frequency. And then you present them as percentages or proportions. For example, in an example you see here is we are talking about in our sample, what is the proportion of smokers, what is the proportion of ex-smokers, and what is the proportion who never smoked. So as you can see, in a sample of 80 plus 70 plus 60, which is 210, 38.1% reported they never smoked, 33.3% reported they are ex-smokers, and 28.6% reported they are smokers, currently smokers. So you see, cigarette smoking, which is a categorical variable, which has some kind of ordering, that is, ex-smoker, never smoked, smoker, ex-smoker, and a smoker are presented as proportions. Similarly, you can report age distribution. Now, when we want to summarize the numerical variables, which are generally on the continuous scale, you can use two measures, which are called as measures of central tendency. One is called as mean, the other is called as median. And then you can also do measures of spread or variability or dispersion by using standard deviation or variance and the range. So the two main formats that we discussed, one is based on an arithmetic principles, that is mean and standard deviation, whereas other one is based on ordering the values by their magnitude and then selecting the values according to their rank or the position. So for example, when you order height of individuals in your sample by ascending order, and then you look at the median value, middle value, that's the median, and so on. So mean, to calculate mean, you don't need to remember any of these formulas. This is for just conceptual understanding. Nowadays, the statistical softwares such as Stata and others do it on a click of a button. So in general, what is a mean? A mean, to calculate mean, all you need is you add all the observed values and then divide by the sample size. That's your mean. For example, we had a data of 65 babies, and we have the birth weight of each of these babies from 1 to 65, and we added all these birth weights, and then we divide by 65. That gives us a mean weight of 3500 05.9 grams. So that's how you calculate the mean. That is your measure of the central tendency. So this is a graphical representation. You have the mean as the middle value, and then the deviation from mean is called as central deviation, standard deviation. So for example, this dot is your mean value. You represent it by X bar. And these small stars are individual values. And you can see there are values both on the both sides of the mean. So that is the deviation from the mean. Now you can calculate the standard deviation. So how do you calculate standard deviation? Again, it's very simple. Once you have the mean, you calculate the deviation of each value from the mean, which is you subtract the values from the mean value. Now, what happens is because you have both the positive and the negative values, they would cancel out each other. So what you do is you square the deviation and then add a squared deviation and then, sorry, and then you square the deviation, add a squared deviation, and then divide by n minus 1 and take a square root. So that gives you a standard deviation. The principle is simple because if you just add all the values, which would be positive and negative values, it will cancel out and you will get a zero value. So once you square them up, all the negative values then turns out to be positive values. But because you have squared them, you have to now take a square root to bring them back to the basic format. So that's how we calculate the standard deviation. Now, remember we said that we have the birth weight of each baby. So let's take example of the first baby. The birth weight was 33,850. 33,880, which is 3,380 grams. And we know the mean weight of the sample was 3,505 grams. So we subtract 3380 minus 3505 and we get a negative 125. We square them up and then we do this for each observation from 1 to 65. And then all the square deviations are divided by n minus 1, which is 64. And then we get a square root. So standard deviation turns out to be 650 grams. So now we know that the mean is 3505 and a standard deviation is 650 grams. So that's how you measure the mean and the standard deviation. But what is the use of this information? So the bigger standard deviation means there is large variability in our data because it measures the spread around the mean value. You could also get a value of 0 for a standard deviation, but that is possible only if all observations are same. And the unit for the standard deviation are same as the unit of the data. And this standard deviation is generally the best estimate of your population standard deviation, which is sigma. And that's what our interest was in the first place, because we derived a sample from the population to infer about the mean value of a particular parameter of interest in the population. Another measure of the variability of dispersion is called as variance. Variance is simply just the square of the standard deviation. And again, just like a standard deviation, it is the best estimate of the population variance, presented reported as sigma square. Now let's talk about the median. And we said the median is based on the principle of a middle value. So in our example of the birth weight, we know that there were 65 babies. So if you arrange the data in the ascending order, the middle value would be 33rd value, which is the median value. So the median value divides the data into two halves. As you can see here, you have all these 65 birth weights, and you can see we have arranged them in ascending order starting from 1890 grams all the way to 5430 grams. The middle value, which is the 33rd value, is 3500 grams, which is the median value. So this is simple, a straightforward concept. When the observations are odd, you just take the middle value. But if you have number of observations that are even, then you take two middle values and divide them by 2. For example, this is an example of the blood pressure, and you can see we have two middle values. And to calculate the median, you divide 95 plus 110 mmHg divided by 2, which is 102 mmHg. So what is the key characteristics of the mean and median, and when should you be using median and when you should be using the median? Well, the important thing to remember is that the median takes into account all the observation. The mean value takes into account all the observations, whereas the median is based on one observation, which is the middle observation. Now, when mean takes account all the observations, it is influenced or it is sensitive to extreme values, or we call them outliers. Whereas because the median is a single value, it's a middle value, it is not sensitive to the outliers. So as you can see, this is an example of salary of a particular institution. And there are 9 staff members. And you can see the salary of 1 to 9 staff members ranges from 14K to 8500K. So the mean would be just the addition of all the salaries divided by the sample size, which is 9. That turns out to be 35,000, say, reals. But as you can see, the median value is only the middle value, which is the fifth value, is 20,000, say, reals. Now, as we see clearly that the most of the staff members are earning between 14,000 reals to say 25,000 reals. But the mean is giving us information that the mean value is 35,000 reals, which is we does not do justice to the data for the simple reason that it was largely sensitive to the extreme values, which is to say the value of the salary of the CEOs, which is 100,000 and 85,000. Whereas the median is giving you a more accurate salary description for this particular organization, which is 20,000 reals. So that's how you have to understand when to use which summary measure. Another way to report numerical data or a continuous data is you can divide them into quarters. You can call them quartiles. So and you have the observation, just like you arrange the observation from ascending order to estimate the mean. The first quartile, as we said, the median value is 50th percent, which is the middle value, 15th percentile, which is the middle value. It divides the data into two halves. So the first quartile, the first quartile, which is 25th percentile, has 1/4 of the values smaller and 3/4 the values larger. That is called as Q1 or the first quartile. Q2, we have discussed, it is a median value, which is 50th percentile. It has half of the values on the either sides. And the third quartile, which is called as Q3 or 75th percentile, has 3/4 of the values smaller than that and 1/4 the larger than that. This discrimination has a very important application, and we'll see that in one type of graph, how these quartiles presents the distribution of data. Then when you use quartiles or median, the measure of spread or the variability or dispersion is the distance between the first quartile and the third quartile, which gives the idea of the spread of the values. And it is simply calculated by subtracting Q3 value minus Q1 value. So that's called as a range. You can think of other categorization based on the ranks, and these are sometimes called as tertiles, quartiles, or quintiles, depending upon how you distributed the data. If you distribute the data into 3 equal categories, they are called tertiles. If you distribute data into 4 categories, it is called quartiles. If you distribute data into 5 categories, they are quintiles. So there's nothing very amazing about it. It's just your purpose. When do you want to use which type of categorization based on the ranks? And then same example where we talked about the median value and the first quartile and the third quartile. Here you can clearly see this is the first quartile in our data. This is the second quartile, which is the median value, and this is the third quartile and the same data of birth weights. Now let's talk about mode. So mode is a value that occurs more often in your data. And the range is difference between the largest and the smallest values. But as we see that it is not very often, very commonly used. Generally, people use median and the mean and standard deviation to summarize data and the distributions. Now let's quickly talk about how do you present this data. So that is, we discussed this about specific presentation approaches for different types of variables. Now let's take examples. We discussed about graphical summary using for the categorical variables. Now you can report them as bar charts. As you can see in the example that we looked at, the age groups between 40 and 49 years, 50 and 59 years, 60 and 69 years, and 70 and 70, more than 70 years are distributed as 41%, 38%, 15.7%, and 4.8% respectively. Now you can convert the same information that is in the table to a more visually appealing format, which is called as bar chart. And you can see here on the right hand side is the percentage of participants in each age group. Here you are reporting the proportions, and these bars are, you can think of as horizontal bars rather than vertical bars. So what we have done is we have reported the percentage of observation in each group. Now you can use bar chart only in situations when you have categories, whether they are nominal categories or ordinal categories. You cannot use bar chart for other kind of variables. Another way to present the same information is you can use a pie chart. You see here again, we have 41%, 38%, 16%, and 5% individuals in specific age groups represented in the pie. But the most important thing about the pie chart is you can use pie chart only when you have mutually exclusive categories. So the age group 40 to 49 and 50 to 59 are mutually exclusive, and you have full information on the denominator. So you know all the entire denominator. If you have missing information, then you cannot use your pie chart. Or if you have non-exclusive categories, then you cannot use pie charts. Let's talk about summary, graphical summary to present the quantitative numerical data. As we discussed about the birth weight of 65 babies, you can present that as a table, but you can also present that in a more intuitive and more visually appealing format, and that is called as histogram or frequency distribution. So what you do is you count the total number of observation, you identify the lowest and the highest values, and you decide on the grouping and the size of the interval. And then again, as I said, these should be mutually exclusive and include all the observations. And then you create a frequency distribution. I'll show you the example, but you don't have to do it manually nowadays. Stata and other softwares do it on a click of button. So these are our individual observations from 1 to 65. Now you group them in meaningful groups which are mutually exclusive. So let's say we created groups of 1500 to 1999 gram, then 2000 to 2499 gram, and so on. And then we put numbers, how many childs are there in each category. So in this category, 1500 to 99, there was one child. In 2000 to 2499, we have two childs, and so on. And you can see that once we create a tally, we know the distribution of number of children in each category. Excuse me. And if you just flip this graph, you can see that you have some kind of distribution, which is called as histogram. And you see this, the same graph has been converted into a histogram. So this is a bar chart that represents the frequency of the percentage distribution. Now you can clearly see the values that are at the bottom, which is on the x-axis. These are the midpoints of each birth category, which we had created. And you see here the number of babies in the first category, which was for 1500 to 1999 is 1. And the next one is 2, and so on. So this gives you a very nice visual presentation of your entire data, which is called as histogram. So the difference between the bar chart and histogram is an important point that you should remember. In the histogram, it is the x-axis continuous. There are no gaps. Whereas in the bar chart, we know that they are based on a specific categories. So there are gaps in between. So that's what you need to know. Now, another application of the frequency distribution or the histogram is, as we know that we want to draw the information about the population from the sample. So when you have a large enough sample, you see the distribution. We'll talk about blood pressure distribution of a sample of 113 males in the first graph, blood pressure distribution of 500 males in the second graph, and the blood pressure distribution of in a population of males. So as you keep on increasing the sample size, you see your histogram goes on becoming more and more sharper and it has a smaller grouping interval, and it becomes more smooth, and it starts resembling your population distribution. Now, that has several important implications, and we'll talk about these implications when we talk about normal distribution. So, the distributions could be symmetrical and bell-shaped. This is also called as normal distribution. Another kind of distribution you could talk about is positively skewed or skewed to the right distribution. Another type of distribution we generally talk about is negatively skewed or skewed to the left. So when do we get what kind of distribution depends upon how the data was organized, or whether the data in the first place data in the first place is uh, skewed or not skewed. For example, how do we know our data is skewed or not skewed? Generally, when your mean, median, and mode all coincide to a common value, that is the middle value, here you can see, you get a symmetrical bell-shaped distribution. So that's your symmetrical bell-shaped distribution. Now, suppose your data, we discussed about that principle in example of the salary. You saw that some members of the staff in that organization had very high salaries. So that leads to the skewness in data. For example, when you look at the mean in that data, we had 35,000 reals, which is, think of it that as this mean, which is much higher than the median value, which was the middle value, which was 20,000 reals. And the mode is the most frequently occurring value here. Now, when the mean is greater than the median, that means the data is positively skewed or the right is skewed. You could have another scenario where mean is less than the median. And in that scenario, you would have left skewed or negatively skewed distribution. Now, the type of the skew or the distribution you would see depends upon the data that you have collected. Generally, the data on several biochemical parameters or parameters such as weight, height, they are generally symmetrical bell-shaped. We don't really see much deviation in that data. But there are certain biochemical parameters wherein, especially in the disease situations, where we see that the data is skewed because of abnormally high values of those parameters in the disease states. You can also see other kind of distributions such as bimodal distribution, and this one of the classic examples of bimodal distribution is you can think of age of presentation of individuals with, say, Hodgkin's lymphoma. They present at a very early age and that at a very later age. And then there are other distributions such as reverse J shape and uniform, but they are not very common. You don't need to worry too much about them. So again, we discussed about the graphical summary of the numerical data. Similarly, you can create graphical summary of the discrete data. Now, in this particular data, we are talking about number of live births uh, for particular women. So here you see the number of women who had 0 live birth, 22 women had 1 live birth, and so on. Now you can again create a similar frequency distribution using this data, and you can create a similar kind of histogram. But the key difference would be, as you know, that the birth is a discrete event. You don't have 1.5 baby or 2.5 children. So that's why you see the gap between these bars. But in reality, on x-axis, you have a continuous scale running from 0 to 10, and you have these y-axis representing the percentage of women with 0 child or 1 child and 2 child, and it is actually a histogram. Another way to present such information is you can add all these frequencies together to get a cumulative frequency. The idea of cumulative frequency is that when you start adding all the proportions, you should get a total of 100%. So that's what you're seeing. So around 30% women had 0 child, around, then you add on to them women with 1 child, it goes on 25%. If you go back to the previous slide, so 35% plus 35% is around 70%, and you can see here 70%. And then you had women with 2 children, which is like 20%. So 70 plus 20 is 90%. That's how you get the cumulative frequency chart. This is another example of hemoglobin. And now we come to a very interesting graphical presentation, which is called as box and whisker plots. So the box and whisker plots helps you summarize the distribution using median and quartiles. So it gives you very good insight in the distribution in terms of skewness and the outliers. So the box has a horizontal line indicating the median and the vertical line that runs from minimum value to maximum value unless there are outliers. And then you have suspected outliers, which are points beyond 1.5 times the interquartile range. So let's look at one of them. We have the same data that we talked about, birth weight of 65 babies. And you can clearly see this is a classic box and whisker plot. So this is the box. The edges of the box represent first quartile and the third quartile. The medial value is the median value, and this particular dot is outlier, which is the baby with 5430 birth weight. So you see, this is a very complicated table with all the numbers, but this is a very visually appealing way to present the birth weight of 65 babies in a box and whisker plot. You clearly see what is the median value, which is 3500. You know what is the Q1 value, which is 3000. What is the Q3 value, which is 4000. You have one outlier, and then you have this full distribution in a simple visual graph. The same graph you can create for the number of previous birth and so on. Another way to present the data is when you have more than two variables and you want to see both on the same graph. So you could have situations where you want to see two categorical variables together, you want to see two continuous variables together, you want to see one categorical and one continuous variable together. Let's look at some examples. This is also called as cross tabulations of contingency tables. In this particular table, you can clearly see we are interested in knowing that there are three villages, A, B, C, and they have three types of water sources, river, pond, and spring. And what we are interested in knowing is what proportion of villagers get water from each of these sources. So you can create this graph, which is a little hard to interpret. What you can interpret is, depending upon your question, is from river, 40% villagers in village A takes water from river, 53% in village B, and 45% in village C. But if you convert them into a bar with A, B, and C villages, and three bars are representing each water source, blue for river, orange for pond, and pink for spring, it's more visually appealing and easy to understand that in village B, with the highest bar, shows that 53% villagers take water from the river, and so on, depending upon your interest. You could be interested in knowing relationship between two continuous variables. Say, how does the weight changes with the weight circumference? So weight change is now your outcome variable and weight circumference is your exposure variable. Now, logically, you would say that the individual with higher waist circumference would generally have higher weight, but you can plot that also on a graph. And you can see here on the x-axis, we have waist in centimeters, and on the y-axis, we have the weight in the kgs. And you can clearly see a relationship that as the waist circumference goes on increasing, the weight of an individual is high. You see that? So that's how you can present two continuous data. You can present categorical and continuous also. You can distribute the weight data into males and females, and you can plot them on the same axis, and you see generally the males have more weight as compared to the women. And then you can make more meaningful graphical presentation by using box and whisker plot. And here you can clearly see that the mean weight in the males is higher than the mean weight in the women's. And also the third quartile and the first quartile are much higher for males as compared to the females. So depending upon your interest, you can create different graphs, but you have to keep in mind the best visual presentation to appropriately show the distribution of the data. So the idea is that you have the data which has both the pattern and the variations. What you want to highlight is the pattern and not the variation. So the goal is to emphasize the signal and de-emphasize the noise. And that's why in the previous example, you can create a scatter plot to show the relationship between weight and gender, but a far more better way to present the same information is your box and whisker plot. So I'll stop here for this particular topic, and then we go on to discuss the normal distribution. Uh, do we have any questions on the things that we discussed for now? Any questions, you can type in the chat or you can feel free to ask me directly.
Yeah, thank you very much, Dr. Habib. So, if anyone has any question, you can either type or you can unmute your mic and ask the question straight away.
Or otherwise, we move to the next important topic.
I think we can move and leave the questions till the end.
Oh, no worries. Thank you very much.
Thank you.
So let's now talk about the distribution again. So we'll start with the normal distribution, and we have seen this graph previously where we try to understand how increasing the sample size helps us get closer and closer to the population distribution. So as we move from the small, sorry, as we move from small sample to a large sample, we see that the variable of our interest, when we present that as a histogram, closely approximates the population distribution. And we can think of this, and you have probably seen this bell-shaped graph several times, which is also called as normal distribution. We talked about positive, negative skewed, and symmetrical bell-shaped distributions. And we have understood what happens to the mean and the median when the distribution is right skewed or when the distribution is left skewed. Now, let's talk about the properties of the normal distribution. So, the normal distribution is a probability distribution. And the beauty of this distribution, it is perfectly symmetrical around its mean. And we have also said that for a normal bell-shaped curve, the mean, median, and mode all coincide. And we know that it is a function of mean and the standard deviation. So let's look at some other variables in different populations. You can look at the height of 8,000 women. The mean is 163 centimeter, median is 163 centimeter, which means that they are coinciding, which means this is a perfectly bell-shaped distribution. We can talk about birth weights of 800 children. Mean is 2787 grams. Median is 2800 grams, but they are so close, you can generally assume that it is a normal distribution. You don't have to worry too much about fine differences. Again, if you look at the hemoglobin of children, the mean is 112 gram per liter and the median is 113 gram per liter. You can consider this as a bell-shaped curve. But when you go to other kind of distributions, uh, when the mean and median are not really very close, then you know that they are either positively skewed or negatively skewed, depending upon whether mean is greater than median or mean is less than median. So that's what our normal distribution is. And then we discussed about the properties. The important thing to also remember is the total area under the curve is equal to 1, which is 100%. We also said that it is a theoretical distribution, which means that no real data will truly be normally distributed at the population level. But we can consider that as a theoretical distribution. And the shape, the most important thing of a normal distribution, is determined by the mean and SD. Now the question is, how does the shape changes with the mean and SD? We know that the standard deviation show means the variability around the mean. So it means that if you have a large standard deviation, your normal distribution would be flatter. Whereas if you have a very narrow standard deviation, then your normal distribution curve should be a peaked curve. Let's look at those examples. So you see, on the left hand side, we are saying that both the curves have the same mean. So the curve on the left has, say, the mean of around 95, and the curve on the right, this one, the red, is mean of 120. So the height is similar because that represents the proportion of individuals in this curve. And you can see it has the same standard deviation. That's why they are similar in nature. You see the graph have the same width in spite of the fact that they have different means. So, but if you look at the right graph with the blue and the red thing, one graph, the blue graph, has a higher peak, whereas the graph with the red color has a lower peak. Now, what it means is that they have, again, because the means are same, they are perfectly coinciding at 120. But because the standard deviations are different, so the one with the larger standard deviation is more flatter, whereas the one with the smaller standard deviation, which is less variance, is peaked in nature. So that's how changing the standard deviation changes the spread, whereas changing the mean moves the curve on the right or on the left of the axis. Now this has implications, and we'll talk about this in the next few slides. Uh, and again, we take the same example of our birth weights of 65 children. The important thing to remember, and that you probably have known before this lecture also, is one standard deviation. We said that the area under the curve is 100%. So one standard deviation around the mean captures 68% of the distribution. Two standard deviation around the mean captures 95% of the distribution. That are the limits of limits according to the standard deviation. So when you get a particular mean value, say 3451 gram, and then you have a standard deviation which is 460 gram, so you would have 68% of the values between, which is 3450 minus 460 to 3451 plus 460. So all those values of the birth weight of the babies would be within the one standard deviation, and it would be around 68% of the total distribution of the sample. So those are the limits of the standard deviation, and it gives us an approximate value of what proportion of data is contained in 1 SD or 2 SD or 2.5 SD. Now, another important concept that we need to understand is called as sampling variability. Now, what is a sampling variability? We talked about the sample. We said that to infer a population parameter, we need a sample. And it's best if we get a representative sample by doing a simple random sampling. But what happens when we do multiple samples, when we draw multiple samples from the same population, you could get a different value for your mean value and your standard deviation with each draw of the sample of a fixed size. Let's take an example. We said that in a simple random sample, each individual in the population has equal chance of being chosen in the sample. That means when you draw multiple samples, there is a high probability that you would have different individuals in the each sample. And that means that your parameter that you're measuring could have a different mean value and could have a different standard deviation with each draw of the sample of a fixed size. So this random sampling helps us control the systematic bias. But the challenge is, even with that, there is still what is called as sampling variability or error. So when we repeatedly choose samples, we get the statistics could have different values. Let's take this example. We discussed about this blood pressure example of 113 men, and you can clearly see that the mean value is 125 mmHg and the standard deviation is 14 mmHg. Now, we decided to do an experiment, and we took 500 separate random samples of a fixed size of 20 subjects each. So your sample one of 20 subjects gave you mean value of 125.7 mmHg and a standard deviation of 10.9 mmHg. The second sample gave you mean value of 122.6 mmHg and the standard deviation of 20.7 mmHg. You keep on drawing samples, and after 500 draws, what you get is a distribution of your sample means. You see here, the distribution of the sample means. So you would have values all the way from 115 mmHg as the mean value, all the way to 195 mmHg as the mean value, and 135 mmHg as the mean value in all the 500 draws. And the beauty of this is, as you can clearly see, that this distribution is again, for this distribution of sample means is again showing what is called as normal distribution. You could do another experiment with now 50 subjects, and you would again get a similar, more or less normal distribution. This time your sample mean is 125 mmHg and the standard deviation is 1.9 mmHg, which is much lesser uh, than 3.3 mmHg. And we know, we have discussed this, that as we keeps on increasing the size of the sample, your standard deviation becomes narrower and narrower. So with 50 samples and 500 draws, you get a sample mean of 125 mmHg and the standard deviation of the sample means of 1.9 mmHg. You again repeat the experiment, now with 100 subjects. What do you expect? A narrower standard deviation or a broader standard deviation? Let's look at it. So this is the first sample, then you have the second sample, and you see here, you have a further narrower standard deviation of the sample means. Though your sample mean is 125 mmHg. So the conclusion is that as you keep on drawing multiple samples of the fixed set, the larger the sample size, you would have a narrower standard deviation. And the beauty is that though the individual value could vary, but the means of the sample means would follow a normal distribution. And you can see that in this box and whisker plot also, mean based on 20, mean based on 50, and mean based on 100. The mean value is more or less same, but the standard deviation of the sample means is getting narrower and narrower. So the key things that we understood from this is that the distribution of sample means tended to follow approximate normal distribution even when the individual values are not normal. And the variability in the sample mean keeps on decreasing as the sample of each mean based upon each mean goes on increasing, and the distributions are generally centered at the true population mean. So the idea is that this was a simulation and we call it sampling distribution of the sample mean. But we don't usually have the luxury of repeating the experiment again and again. For example, the same experiment that we discussed just now. So in a real world, because it is not possible to do multiple draws of the sample to understand what is the distribution of the sample means and what is the true value of the population parameter, you use what is called as a mathematical framework, uh, which is called as central limit theorem. And it is a very powerful mathematical tool. And it says that the sampling distribution of the sample means based on all samples of the same sample size is approximately normal, regardless of the distribution of the original data in the population. So that's what we just discussed and we saw using sample of 20, 50, and 100, and we saw the distribution. And that's what the central limit theorem also says. Now, what is the use of central limit theorem? When we say that the mean of all the samples in the sampling distribution is true mean of the population parameter that we were interested in. So the standard deviation in these sample means of size n is equal to sigma over under root of n. We also call it as standard error. Now there is great use of this concept of standard error because as we see here in our previous example, when we had three different sample sizes and we had the means of 500 samples versus means of 5,000 samples, we clearly see that more or less the mean value of the population parameter is similar, which is around 125 mmHg. But as we keep on increasing the sample size, we saw that the standard deviation of the samples goes on decreasing. So the standard deviation, you look at the last column, of the sample means is also called as standard error. And when you estimate it by using central limit theorem, you get the same or approximately similar values as we get by using the simulation. So that's the beauty of the central limit theorem. Now, what is the application? The application of this theorem lies in what we call as quantifying the uncertainty around the population parameter, or quantifying the uncertainty around the parameter of interest. So central limit theorem said that when taking a random sample of continuous measure of size n from a population with the true mean mu and the true standard deviation sigma, the theoretical sampling distribution from all possible sample would be like this. So that is your distribution. This is mu, and this is your distribution of the mean value. Now, this information, well, using the properties of the normal curve, this shows that for most random samples, we can take 95%. The sample mean will fall within the two standard errors of the true mean. So we drawn the sample from the population to know the population parameter, let's say the mean height. Now, what we are saying using the central limit theorem is that 95% the sample mean will fall within the two standard error of true mean. So we don't know the true population parameter, but what we know by using central limit theorem is that within the two standard errors, the true population parameter resides. So that takes us to another concept, which is called as let's take this example. So if we start at a mean value and go to standard errors in each direction, the interval that will create will contain the mu, which is your population parameter most of the times. So that is also called as long run probability concept. So that helps you understand that what is a confidence interval. So such an interval is called as 95% confidence interval for the population mean. And we know that we can derive this by using central limit theorem. There are newer concepts, newer terminologies for confidence interval. They're also called as compatibility intervals. They are also called as divergence and so on. Dr. Sohail will talk about these in the next lecture. But for now, in the simplistic terms, what we're saying that if we use the concept of long run probability, if there are 100 random samples of size and taken from the same population, 95% confidence interval computed using each of those 100 samples, 95 of 100 intervals would contain the true population parameter. So the idea is that still 5 will not contain the true population parameter. And also we don't know of these 95 which of the interval has the true population parameter. But it is helpful in quantifying the uncertainty. So you look at this example, this is a simulation based on the blood pressure of the males of sample size 50, and then draw 100 random samples. And you see this is the mean value, 130 mmHg, the blue line. And you see the 95% bends around that mean value for each different sample. So you can clearly see that there would be some samples which are not containing the true population parameter, whereas others are overlapping with the true population parameter. So the technical interpretation is if you 195% confidence interval would, if you compute using the same approach with the standard sample size, the same sample size, 95 of those interval would contain the true population parameter. But the important point to note here is that this is one of the interpretation based on the long run probability, but we rarely have this luxury to repeat uh, the analysis or repeat the experiment. So you can't actually rely on long run probability interpretations. We use a different concept which is called as probability density function, which also gives a similar indication and which tells us that uh, if you use that probability density function, you know that 95% of the central values around test statistics would not be unusual under your null hypothesis based on your based on the research hypothesis that you started with. So we'll talk about those concepts in the next lecture, but the only takeaway from the central limit theorem is it helps in quantifying the uncertainty, or it helps in quantifying the sampling error. So confidence interval only accounts for random sampling error, but cannot help with other systematic sources of error or bias. For example, the systematic sources of error or bias in the example that we have discussed using the blood pressure could directly arise from an incorrect instrument, which is always measuring BP incorrectly at all times, or it could be because of people who participate in your survey uh, are volunteers, and there could be those who volunteer to get their BP checked, and there could be those who don't want to get their BP checked, so that could lead to selection bias. So you cannot actually remove the systematic error by using the confidence bands, 95% confidence interval. You can only quantify the sampling variability. And few notes on confidence interval. Are all confidence interval 95%? No, you can actually choose what limits you want to use for confidence interval. You can use a 90% confidence interval, you can use a 99%, but generally 95% is more commonly used. And we know that these are based on our central limit theorem, and we know that 95% confidence interval, you need two standard errors. You need a value that is your mean value plus or minus two standard errors. One last point about the difference between the standard deviation and standard error. So we discussed about mean, and then we said then the standard deviation is the measure of dispersion or deviation around the mean value. So it refers to the variability in the individual observation in a sample, whereas the standard error of the mean is also a measure of the standard deviation, but it is not for the individual values. Rather, it is the variation in the multiple sample means computed on multiple random samples of the same size taken from the same population. So when we talk about standard error, we talk about samples that have been drawn, uh, samples of the same size that have been drawn from the population. Whereas standard deviation only refers to the individual observations. I'll stop here. And if we have any questions, we can discuss now.
Thank you very much, Dr. Habib, for such a comprehensive review of those foundations and fundamentals concepts in biostatistics. It really covered everything starting from very basic, taking the audience through different levels of data and the variables, the measures of central tendency and measures of dispersion. So really, thank you. So now the floor is open for any questions.
Well, I haven't touched upon the statistical tests, but as we discussed about the distribution or the classification of the variables, in the most simpler terms, those variables determine what statistical test to be used for each variable. So we can discuss them sometime later. But again, just like the classification of variables determine how they should be presented in terms of measure of central tendency and dispersion, the same criteria applies which test to be used for each type of variable. For example, chi-square tests are used for categorical variables, and you can use t-test and ANOVAs for your continuous variables and so on.
Yeah. Uh, Yeah, thank you very much. So if there's no question, I just want your opinion, Dr. Habib, about the central limit theorem. My
Uh-huh.
understanding before is for central limit theorem is that whenever we have a sentence like a sample size of 100 or something like that, we just assume normal distribution. So how far this statement is correct?
I mean, that's a great question. I mean, generally, we actually, for parametric estimations, I mean, even 20 for a continuous data, the data that is measured on continuous scale, I
Mhm.
mean, even sample size of 30 or 40 is good enough. You don't really have to
Okay,
wait for 100.
400. Ah, I see. Okay, okay,
Yeah.
yeah, yeah.
Yeah,
That
that's the beauty of central limit theorem.
hmm. Yeah, because as you mentioned, this will have its implications on the statistical test that we're following, and this also will have their implication on the results and the reporting and interpretation of data. So these are
Absolutely.
very basic things. If they need to be managed very cautiously and meticulously in order to have the best evidence possible out of the data.
Absolutely.
So still no more questions. Apparently everybody I saw some thumbs up and some
Yeah, but
hearts.
I mean, just to add, I mean, the students can feel free to actually send me email also if they figure out some questions later while they are doing research or whatever. I mean, sometimes it's hard to actually absorb all this information in 1 hour
Yes.
and then also have the same questions. Probably when they reflect on the lecture using the recording, probably they might have few questions.
Yeah, sure, sure. There is one question here, or just maybe just a suggestion. I would like to know
Uh-huh.
if you would also touch on data cleaning before running a statistical test.
Uh-huh. So, so generally, what is more important than actually cleaning is to understand the data. So what happens is if you are doing data cleaning in Excel, you are prone to do a lot of errors. So the best to wait for data cleaning is actually have the data in Stata and then using Stata commands and do files to clean the data so that you know what you have done. The advantage of using a do file is actually reproducibility, and also it's good for purpose of sharing. For example, if you get stuck at some place and you want to figure out if you are doing correctly or incorrectly, you can always share your do file with your supervisor or your colleague, and they can help you writing those commands and checking if you are doing it correctly or not. So that's how we see the data cleaning thing. Uh, so it is more about making sure that you don't do errors by creating errors in existing data while you're doing cleaning. So it's best to use do file and as data.
Yeah, thank you very much. I hope that clarifies the question, Azza. So do you have any more questions? I know we are behind on time, but the topic and the way it was presented, I think it's worth going beyond the time, and I think everyone is benefiting out of it.
So if we don't have any further questions, thank you very much for your time and attention.
Yeah, thank you very much, Dr. Habib, for your time and for the very detailed presentation, and I think everyone has benefited out of it. Thank you very much.
Thank you. Assalamu alaikum.
Wa alaikum assalam wa rahmatullah.